Good morning, everyone. Today I'm Isaac, and today I'm going to present on the Latin hypercube sampling, or let's say LHS. So we often use the Monte Carlo simulation on reliability analysis, but they can be incredibly computationally high cost. So today I'm going to explore some other method, for example, this hypercube sampling, Latin hypercube sampling, which is often a superior alternative, and how it works, and I'll crucially compare the performance against the Monte Carlo simulation with two specific cases study from our coursework. And so let's start. So here are the table of contents, and let's start. So why do we need a new sampling method? In risk assessment, our goal is to propagate the uncertainty. So we'll have many inputs of loads and material strength, and we'll have to find the probability of failure. And the standard approach will be the direct Monte Carlo sampling, because actually Monte Carlo sampling is like randomly throwing darts on the dartboard, and it will work eventually, but it's not efficient. So because the computational cost will be high, because like for example, to reduce the error by 2 times, you will need 4 times of the samples. So there will be a huge computational cost. That's why we need a new strategy on sampling to reduce the sample required. And the strategy introduced here will be the LHS. So what is LHS? Basically, this is a sampling method which is designed to ensure that every portion of the probability distribution is sampled at least once. So you can imagine that you have a n by n chessboard, and you want to put n chess on the chessboard so that there are no chess like sharing the same row or the same column. And this is actually exactly what the LHS will do with our data. So it will guarantee that we have exactly one sample in every row of probability and every column of probability. So it will prevent the crumbling, where we accidentally test the same scenario twice and eliminate the gap between missing a scenario. So as you can see right here, on the left one will be the random sampling using the direct Monte Carlo. So right here, you can see that there will be some clumping, while on the Latin hypercube sampling, there are no clumping. So each row and each column will have one sample there. So it's more evenly distributed, so it's like kind of better. And after introducing what is like Latin hypercube sampling, you'll want to know how to do it. So basically, it will be some three-step cases. So the first step will be certification. We'll define the probability access from like 0 to 1 into n equal spaces. For example, if n equals to 10, it will be like 0 to 0.1 and zero point 0.1 to zero point 0.2, and then so on. And the step two will be the inverse transformation, which is like we randomly pick one probability value from the inside of the interval, and then map this probability back to the physical variable using the inverse CDF, which is actually similar to the Monte Carlo simulation. And then we'll do the random pairing. And then this result will be a input matrix where the single variable has been fully explored across its entire range, and then combine it into the in a random way. And what's the key advantage of it? So basically, it will reduce the noise in the simulation, and the mean and the standard deviation will approach to the true value much faster than the Monte Carlo simulation. So for example, in this case right here, it for LHS, it converges at like 40 samples, while the Monte Carlo simulation will converge at like about 320 samples, which is like 8 times faster than that of Monte Carlo simulation. So After talking about many of how to do it and then what's the key advantage, we'll have some case study. For example, the assignment 5 by LSH and Monte Carlo simulation. So in this case, we'll use the beta FORM value as a true value to compare the probability error, the calculation error by the LSH and the Monte Carlo simulation. So the result will be right here, which is clear that the Monte Carlo simulation, like direct Monte Carlo simulation, will need much more samples than that of LHS. Like for example, right here you have like uh 200,000 samples for Monte Carlo simulation, while the LHS will need like only 75,000 samples to do to calculate the probability of failure. And then it will converge much faster, as you can see right here. And estimation is actually more or less the same. Both of them are like 8.5 to the as like 0.008.5 have a probability of failure. And the error is actually small. It's acceptable. And you may think that, oh, LHS is so good. And but why in the class we don't introduce LHS? Because it's not a magic bullet. And this will lead us to the case study 2, which is the assignment 3.3 by the in this year. So we'll use the important sampling value as the true value. So let's see. In this case, you can clearly see that for LHS, you need much more, like about 2 times of the samples than that of Monte Carlo simulation. And why? Why we need so much samples for LHS? It's because this is a corner problem. Here, LHS will lose its advantage, but both methods will for LHS would need much more samples than that of Monte Carlo simulation because the stratification ensure that the sample is like evenly distributed, right? But the failure only occurred at a tiny corner in the probability space, like this one, only occurred at this red box, which is like a high-low plus a low resistance. And because like the LHS will pair the variable randomly and it's like evenly distributed, so it will miss this specific corner just as often as the random Monte Carlo does. And in these cases, it's not good to use the LHS. So for to conclude, basically for common events like the probability of failure is like smaller than 0.1 but larger than 0.001, we can use Latin hypercube sampling, which is more superior. Like we only need like 0.4% of the 0.40% of the sample than that of Monte Carlo simulation. But for rare events, it will fail to have to reduce the computational cost. So for this from these samples, from these examples, we can conclude that we can do the method selection guide. So which is like that for the Latin LHS, it can be used for some general statistical analysis and the problem with moderate failure probability, which is like from 0.01 to 0.001. And for Monte Carlo simulation, it will be good, and because like if it's not good, in the class will won't be taught, right? So what's good is that the coding is actually much simpler than that of LHS. Because like LHS, you have to divide each spaces into even spaces, and you have to do many of them, many things to do such problem. And for the rare events, like for example, the assignment 3.3, we can use the importance sampling which is the mandatory choice for high reliability problem, which is like a rare event, which can offer massive efficiency gains where the LHS will struggles. And yeah, basically that is the end of my sharing. And here are the references, which also include the McCabe's paper, which is a really original work published at 1979, which invented this method. And this is the end of my sharing. Thank you.